We are at 11:02 a.m. So we are going to go ahead and get started here while I see several folks still joining. All right then. Nick, John, you guys are ready? Good morning, good afternoon, and good evening to everyone joining across the country. A big warm welcome to all of you joining us on our first KETOS Cooler Chat. I'm Meena Sankran, founder and CEO of KETOS, a water intelligence company enabling operators with innovative water monitoring solutions for actionable decision-making in your daily operations. I'm very excited to share that we will be discussing an important issue today for all municipalities around pressure reducing valves, automated control valves, and everything you could possibly want to know in that realm. To dive into this topic, we have two panelists joining me, Nick Martinez and John Davis, from one of our expert partners in this space, RepMasters. A little bit about their backgrounds and the value that RepMasters provides to its customers. Nick has over 19 years of experience in the waterworks industry, and much of that time has been spent at Demo Water, specializing in construction, PRVs, system operations, and capital projects. Now employed by RepMasters, Nick is able to assist engineers and municipalities with operations, design, inefficiencies, and troubleshooting. He's also a devoted husband and father of 3 daughters. Welcome to the Cooler Talk, Nick. Our second panelist today, John Davis, who has 17 years of experience in sales and operations management, coupled with 8 years of service in Marine Corps as an intelligence analyst. He's an experienced instructor and trainer. He's also worked extensively with municipal and consulting engineers on specifications, design, and applications of high-valued engineered products, such as flexible pipe connections, pipe restraint products, joint pipe for trenchless HDD, pipe bursting and boring applications, as well as flow control valves to include automatic control valves, commonly known as AVCs or PRVs. Both Nick and John's passion and drive for excellence has carried them into irrigation, fire line, plumbing, and HVAC fields. Net, these are two folks you want to have on your speed dial if you're a utility. Both Nick and John are part of the elite team at RepMasters, a company that has been in business for 30 years. They're headquartered in Denver, Colorado, with locations in Montana, as well as Salt Lake City, Utah. RepMasters, if you've not heard of them or if you're not too familiar, they work closely with municipalities, utilities, contractors, facility owners, operators, and engineers in supporting their sort of different manufacturers and products that they carry at the field level, as well as in terms of technical assistance, specification support, product training, everything that you can imagine as a trusted advisor, including field service, and especially if you're doing new product development aimed at solving some of the most challenging problems faced in the industry today. So without further ado, and without me taking the time, I would love to pass the ball here to John Davis and Nick Martinez, who will be covering a training session and followed by a Q&A session that we will be moderating. John and Nick will also tell you a little bit more about the training credits, and we can certainly, if there's anything unanswered, we'll make sure that we get to it to the end. Please enter a lot of your questions in the chat window or in your Q&A window. We are going to make sure that we get to the answers, and if there's anything unanswered, we'll do a follow-up later, okay? So with that, thank you, Nick and John, for joining on this panel, and I will pass it on to you.
Good morning. First off, I want to thank you all for being here. I think this is fun and an exciting course for us because we're kind of water industry nerds, and this is the kind of thing that we really enjoy. First things first, before I hand it over to John, as far as the training units go, we're going to go ahead. We're signed up with CCWP to go ahead and provide training units for these courses. And is how this works is typically in the past, you'd have to upload your certificate, and that's always been a difficult thing, especially with the transition to CCWP. So we figure out a way to where I can just go ahead and upload a roster of everybody that's attended today. So all I really needed was the email addresses of all the attendees today, and I can upload that roster into CCWP. And at that time, they'll send a notification, or you would just log into your CCWP and you would accept those TUs. And this one's for 0.15 TUs. And, you know, as we all know, it's hard to get these, and especially through COVID. And yeah, so if you have any issues with the TU part, feel free to reach out to myself or John, and we'll go ahead and work you through that. We'll go ahead and get going on this thing, and we'll let John start you off.
All right. Welcome, everybody. So we'll just dive right on in. What we're going to be talking about, PRV knowledge, issues, solutions. Thank you for the introduction, Mina. So diving right in. So what is a PRV? When you look at all the different valves that are out there, generally speaking, in this industry, in my experience, it's pretty much anything that looks like one of these, everyone calls a PRV. The reality is, there's a various number of different applications and functions. And once we start kind of taking away, depending on those functions, in this illustration, we really only come down to 3 of these as being an actual pressure reducing valve, or PRV. And again, that's just based on the function. A PRV is simply a function of, or an application of, an automatic control valve, or an ACV. Sounds pretty simple. And an ACV, it stands for automatic control valve. And there's a few characteristics that really determine what an ACV is. It needs to be hydraulically pilot controlled valve, diaphragm, or it could be a piston operated valve. And then it's a valve that's actuated or powered by line pressure differential. And so a PRV is just simply a function or a type of ACV, or automatic control valve. And again, you may know these commonly as PRVs, clay valve by a brand manufacturer, clay valve, Singer, or in this case, you have John Tedder, who is a manufacturer's rep out here, who was the clay valve rep for about 20, 30 years. And just due to his extensive knowledge and assistance, people just started calling them Tedder valves. Or you might hear pilot operated valve, or maybe a diaphragm valve. But all these are terms that are commonly used when we're talking about an automatic control valve. And the purpose is the functions, the different functions, and you'll notice here, the 4th one down, there's your PRV, a pressure reducing control, where we're looking at maintaining a constant downstream pressure. It could also be a float control, or like an altitude control, where we're controlling level in a tank or reservoir, or a solenoid control, where we're doing on-off, simply the valve's either closed, drip tight, or it's fully open. Could also be a flow control, where we're actually regulating, we don't really not necessarily care about pressure, but now we're looking at our rate of flow. We want to limit or have a minimum of 300 gallons a minute, not to exceed 500. Then we're looking at a rate of flow control, or it can be a check valve, or a pressure relief. We can be sustaining or holding a minimum back pressure, or upstream pressure. And again, altitude valve, whether it's an elevated storage tank or underground. And then we can look at pump control, where we want to maintain, we want to keep that pump on its curve for efficiency. And then also we definitely want to have that pump start on against a closed valve. And then we want to control the rate at which that valve opens up. And then at time of closure, we want that valve to slowly start closing. And then Once that valve closes, turn off the pump. So there's various other applications, or it can be a combination of different applications. So there's quite a few different functions. And when we look at our introduction to fundamentals, we like to call it removing the voodoo. A lot of manufacturers over the years have benefited from keeping the voodoo in the valve. A lot of guys will look at these things and they think something might be wrong. And so they'll kind of keep that mystery in there. No one wants to work on it. You know, you see this valve with all this pilotry and this tubing and accessories on there. It looks like a ticking time bomb. So we like to remove the voodoo. These are fantastic tools, and they're vital in the distribution system. And the more you know about those valves and how they operate and how they function, the more apt you are to utilize these valves, you know, to the best of their ability for your system. And when we look at what makes an ACV, it's just a combination of two different components. We have our main body valve, which is nothing more than the most expensive spool piece in your system if you were to remove all the guts out of there with a bridge wall. And then once we add any number of or combination of pilots, accessories, could be a speed control, could be a pressure reducing pilot. Once we put these controls on there, these accessories, along with that main valve, now we come up with an automatic control valve. And the fundamentals is very simple, just like in elementary school and math. You get your input-output box. We're going to take a inlet pressure or inlet medium. It doesn't have to be pressure. It can be, we're regulating you know, flow. We're going to take our inlet, and then based on those controls, you will have a different outlet, something that you're regulating or controlling, and it could be as simple as on-off. And so we look at basic valve construction. We talked about the main valve component, and we have our main valve with its cover or a bonnet. So there's really two pieces here. And then you have internally your disc and diaphragm assembly. I like to refer to this as the guts of the valve. And then you have your seat, which is going to run right along here, and then your main body of the valve. And that is the construction, and we are the representative for Ames Watts in Colorado, Wyoming, Montana, and Idaho, and Utah for Ames as well. So these slides are all kind of based on the courses and instruction that we give, but it really doesn't matter what the valve is. If you're familiar with clay valve in your system, then this particular valve that's referenced, the Ames or Watts Mustang series, is 100% compatible. It's interchangeable with clay valves, so you'll notice same dimensions and interior design. But all valves, all control valves, will follow this basic principle. You'll have your main body valve, and then you'll have your internals. You have your cover, your internals, and your seat. So it works on any. The fundamentals apply to any valve manufacturer. And here's just a good shot of, again, I call this is the stem assembly, which I refer to as the guts of the valve. And then that seat, that stainless steel seat that is gonna make that drip tight seal against its quad seal. So now looking at the operating principle, operating principles and how the valve works. It's not any different than the principles of a backflow or reduced pressure zone assembly. What we're doing is using water, and then we're using that pressure with a surface area in order to apply physics here. So in this case, you have a 1.5 to 1 seat ratio. So 1.5 times the surface area on that top, in that top chamber, to 1 on this would be your inlet, on to 1.5 to 1 on its incoming or at the seat. So in this example, we're using a 4-inch valve, and we have 100 PSI. So we know that force is surface area times pressure. So with 19 square inches on the top, we have 13 square inches on the bottom or at the seat. So as we would put water onto that cover of the valve, our downward force becomes 1,900 pounds, and with 1,300 pounds pushing up. And it's just simple physics at this point. The bigger guy wins. So that valve has to go closed. Conversely, if we remove any of that downward force, and it goes below 1,300 pounds, that valve has to come open. And whenever we're doing these instructional courses on PRVs or ACVs, I always go to this valve will do 3 things and 3 things only. The valve closes, it opens, and it modulates. That's the only thing the valve knows how to do. And if we put water onto that cover, that valve has to go closed. If we take water off of that cover, that valve has to go open. Now, once we start regulating water on, water off the cover, now that valve begins to modulate. So 3 things and 3 things only: close, open, and modulates. So putting this into illustration, if we were to have somebody, which it's obviously not practical 24/7, to be sitting at a PRV with nothing but a ball valve on the inlet, putting water onto the cover, and a ball valve taking water off the cover. If we put someone on there and they just throttled those ball valves, right, that valve would modulate. The question comes up on the difference between domestic and fire. There really, the only difference is that UL dictates that you can have no isolation valves. There can be no potential shutoff on that valve. So the valve will come from the manufacturer. They're preset per UL at 165 PSI, I believe, is for fire. But you will have no isolation valves on there because per UL, there can't be anything on there that will restrict or shut off flow. So it's a good question. That's also why these valves fail open. If that doesn't answer the question, please let me know. So coming into here, we talked about throttling those ball valves and modulating. Here, if we close that downstream ball valve, once we discussed before, you can see we have just over 100 PSI on the inlet. And then we are closed, drip tight, and nothing on the downstream. And if we do the opposite, which is the big no-no, don't really ever want to do this, and we close that upstream. Here, luckily, they have this thing only set to looks like about 50, but you'll notice that valve has to go wide open. And now whatever pressure we have on the high side is now on the low. Which could be pretty damaging if it's 200 to 100. So once we go into the theory of operation, we've discussed the operating principles. And so in this case, we're going to be looking at a pressure reducing valve, PRV. So as opposed to the previous where we had, a ball valve, there's 2 ports up here. We had a ball valve putting water or controlling if water goes onto the cover, and then a ball valve coming off, controlling if water's coming off of the cover. Now all we've done is we've substituted that with a pilot control. In this case, being a pressure reducing valve, this is a pressure reducing pilot. And this pilot is normally open. And I like to put this image here, kind of like a bouncer at a nightclub where it's full of capacity. You have 3 people come out, they leave, and then this guy lets 3 people come in, and then 5 people come out and leave. This guy lets 5 more people come in. Similar type of deal where this guy right here is the brains of the valve. And so what this regulator is sensing, or this pilot, is downstream pressure. It only cares about what's going on downstream of the valve. And so as we set this, if we set this at, let's say 100 PSI, So once we use there's an adjustment bolt on the top here, and we have to be flowing under flowing conditions, and we go to set this. What will happen is if downstream pressure is below the set point, okay, it will go ahead and the valve, since it's normally open, that valve will modulate towards open. Once that pressure exceeds the set point, this pilot will sense that, and then that will go ahead and start closing that pilot, which will then modulate the control valve towards the closed position to maintain the desired downstream pressure regardless of flow. So again, we discussed this, and I have this here again to show that we can have a number or multiple pilots on here. We can have a combination of them depending on what the application is. But typically you'll have on-off valves either going to be open or it's going to be closed. And then we can have modulating or regulating, and we can use, so a solenoid is typically used in an on-off application. However, you can have a electronic valve that will go ahead and pulsate your solenoids so that it's gonna go ahead and modulate that, and you can electronically control the desired pressure reduction if it's a PRV. And here, a combination. So you could have, in this case, a pressure reducing valve that you wanted to have a solenoid on-off feature on there. So you could control, let's shut that valve down, and then when the solenoid, if it's, let's say it's energized to open, once that solenoid is energized, and at that point, now that reducing pilot's gonna go ahead and regulate pressure. So, as we discussed this, here's a 24-inch automatic control valve, and it doesn't matter the size of the valve, but this pilot right here is the brains, and it's going to be telling this 24-inch valve what to do. And again, all we're doing is shuttling water on and off the cover. So when we start looking at a direct acting, and typically in waterworks utility, we hear PRV, we think of the valve on the right. When we're looking in commercial and even in commercial HVAC plumbing applications, PRVs are going to be they're going to be direct acting regulators. And there's a big fundamental difference. And I don't, obviously in the waterworks utility side, the only time you may see these is in front of a residential meter where you're reducing that pressure, low consumption, at the point of use at the home. And there's a big difference between these valves in the way they operate. So a PRV, direct acting, which is also a pilot, is a type of direct acting PRV. This valve is going to be spring dependent. And what I mean by that is that the water itself has to overcome the force of this spring. And so as in this case, if we're looking at a reducing valve that's normally open, that downstream pressure, if it's above the set point, it will go ahead and push up and close that direct acting. Whereas in a control valve, it's only spring assisted. There's no adjustment bolt, like on a direct acting, where if we turn that clockwise, we'll raise the set point counterclockwise. But we use this valve in order to either modulate the closed or open when it's a control valve. And as spring assisted, this really is only there just to help keep that stem on guide and center. If we were to remove that spring, the valve would function, generally speaking, would function like normal. It does allow, sometimes it helps to, if that valve is closed, is fully open, it helps to kind of nudge that back towards closed. But it is not spring dependent like a direct acting. And again, this will show that example as this pushes up, and then that will go ahead and close that direct acting. And again, here, we're allowing for free flow. And the result of this, because it's spring dependent, is that you have fall off, which is ASSE 1003 is the governing principle for fall off that all direct acting regulators, PRVs, must abide by. And it gives guidelines, and it has a minimum zone performance that as flow increases, as demand increases, pressure will drop. And so here in the red here, you see the fall off curve for a direct acting as opposed to an automatic control valve. And really there is little to fall off until you get to a point where you exceed the capacity of that valve. And I won't sit here and read and bore everyone with the slides, but if you look at there, all that this says right here is you have the two biggest differences between these is that a direct acting or regulator is incapable of maintaining a desired pressure set point regardless of demand. So as demand increases, that valve is incapable of maintaining or holding that desired pressure. As opposed to an ACV or an automatic control valve, pressure reducing valve, that will maintain that pressure. You can set that and it'll maintain that desired pressure regardless of flow, as long as you're not exceeding the capacity of the valve, which again is very high. I got to think this has got to be a joke, although I've seen close to similar valves like this, and here's part of that attack of the VOODOO. I don't think anyone wants to touch that thing. So when we talk about automatic control valves, and we get into the issues and problems that are associated. I had to throw this one in for my 13-year-old son. Big fan of The Office, but size matters. And when we talk about that, the number one problem, without a doubt, that we see on these as a manufacturer is line sizing valves. And by that I mean, typically common practice for an engineer is you have an 8-inch pipeline, so we're going to put an 8-inch valve there, 12-inch line, 12-inch valve, and where we run into those issues is the capacity of these valves, and velocity is a great deal to do with that. When these valves are by design, these valves are designed. If you look at any of the manufacturers, their CV charts, flow charts, they'll give you a kind of a set parameter, and the basic guideline is usually somewhere between 20 and 40 psi as your delta P, which is your pressure drop. Meaning, if I want to have 140 on the inlet, and then I want to reduce down to 100, there's a 40 differential, or the delta P would be 40. And so these valves, the other baseline there is velocity. And by design, typically that medium baseline is somewhere between 20 to 25 feet per second. Now, for an engineer on a pipeline side, everything that they've been taught, somewhere between 9 and 11 in a pipeline, that's kind of going to be your guiding principle. Anything over 11 is kind of the danger zone. But these valves, because they operate on line pressure differential, we need that velocity, and automatic control valves, they work best when they work the hardest. And there's another slide where we talk about what position of valve opening we want to be in. But basically that sweet spot is to be somewhere between somewhere over 20% of closed, and then less than 80% of fully open. And that's where we like that valve to be operating, whether it's from the minimum to the maximum flow. When we get below that, what we do is, not unlike putting your thumb on a garden hose, is as we restrict flow, we increase velocity. And in this case, this valve was operating just off the seat. And you can see what it's done here to this quad sealer, this seat, which is it looks like it's supposed to look like a rectangle, but in this case, that flow has chewed that up and almost vulcanized that, into that disc and disc retainer. And then you can see we start getting this wiring effect. This valve will not close. So one of the basic troubleshoots that we do when we come up or we're trying to assist a municipality, first thing we'll do is we want to close the downstream isolation valve. We want to verify the valve is doing the three things: closing, opening, and modulating. And if we go to close that downstream ball valve and that valve does not close, then oftentimes, especially if it's been operating just off the seat, the issue is that valve cannot close drip tight, which can cause several other issues that we'll go over. Another issue we see is cavitation. And a general rule of thumb is going to be 3-to-1 ratio. So if you take your desired outlet pressure, whatever that is, and you multiply it by 3, as long as that's below your inlet pressure, then it's kind of a basic rule of thumb. You're probably safe. If you're close, then you might want to check it. Every manufacturer will publish a cavitation avoidance zone chart, and you can simply take your inlet pressure, in this case 170 psi, and looks like, I don't know, 74 psi, and where those two cross is going to be where that valve performance, where that's operating at. And here you're safe. As you approach that cavitation zone, those valves will get noisy, and we want to avoid constant operation close to or inside of that zone. Here's an example of, in this case, cavitation was accounted for. This is a cavitation control cage. Stainless steel because stainless steel is more resistant to cavitation. So cavitation was accounted for here. The problem was, this is a 6-inch valve, and it's a relief valve on a 6-inch line. And on a relief valve, we're only needing to open up just enough to relieve the excess pressure. So usually we'll account for half of the flow rate is what we want to calculate on there. And in this case, you can actually see it was the velocity that really caused the damage on this. Here's that quad seal, and you can see where it's rectangle here, but as we approach this section, it started to eat away at that seal. And then where this valve's been operating at is, the valves are about, the full stroke is 1/4 the size of the valve. So if we have a 12-inch, if we have a 12-inch valve, then the difference between closed drip tight and fully open is 3 inches. So by measuring this, we can tell this valve is operating somewhere around 7% of open. And you can see this flow path that matches right where, because the slot design is kind of curved, and what that ends up, the impact that has. Again, this valve will not close. And there's, I know every manufacturer will have, they have the ability to go in and size these if we know what the maximum possible or continuous, and then our minimum flow rates are going to be, and we know what this will come into our pressure drop or our delta P. And then we can use published CV factors on these valves, and we can come up with a pretty close to accurate percent of VP or percent of valve opening. And any of those manufacturers can do that. And we look at design is another issue, whether we're looking at cavitation, having to account for that. You'll have, a lot of times we see this parallel where you have a high flow and a low flow. And oversizing also comes into play here. So again, kind of expounding on that, and this is where I'm going to have Nick, come in and take over and wrap this side of this up. But oversizing, replacing that ACV operation outside of ideal valve position. And we discussed that. We want that to be above 20% open and not exceeding 80%. Now, really we just, as long as we don't want to ever be below 10%. 20 to 80 is ideal, but 10 to 90 is manageable. And constant operation outside of the ideal percent of VP is where we start running into damaging issues. And we talked about efficient design practices, and we saw those different configurations. Designs don't effectively address high-low flow. So if you have a 12-inch valve And these valves are supposed to be set at different pressure settings. So you'll have your smaller valve that will handle your lower flows. We want that set at a higher set point than the larger valve that is supposed to sense a pressure drop when that valve can't keep up, and then opens the larger valve. Now, if they're either set too close, or if that larger valve, it'll put that larger valve to where it is actually operating and it's operating just off the seat. When that valve needs to close, when you have low consumption in the middle of the night, kind of reason why those breaks start to happen there. Then we start running into issues when that valve won't close and it's still allowing high pressure into the system. And from here, I'll let Nick, with his experience at Denver Water, take over.
All right, so, what's that? Yeah, I kind of get the fun part of this. My history and background is operations and maintenance. So preventative maintenance and a lot of the common issues are things that I've always struggled and argued with engineers about. And, that's kind of what motivates us to be here, is to kind of find solutions and be a resource for everybody out there that doesn't know a lot about ACVs and PRVs. The biggest issue that I see once a valve is installed is the lack of preventative maintenance. I think there's many water districts and municipalities that don't know enough about these valves to have a good PM program. And over the years, through experience, we've honed and developed what we feel is the perfect PM program. So, one of the issues with not having a PM program is that lack of knowledge, and, not having standard procedures from a municipality to understand what's needed and what's necessary for that PM. These valves are one of the most riskiest parts of a distribution system because they do fail open. When they fail open, almost always they cause main breaks, they cause damage to your system and to different assets within the system. So, and because these valves fail open, this typically is caused because of clogged ports, clogged strainers, or broken fittings. It happens all the time, and if you're not in your vaults, at least inspecting your valves once a year, you can almost expect that this is going to happen. The next issue with these automatic control valves is if you can't see them, you don't know what they're doing. If you can't control them, they're going to control themselves. And yes, they're automatic control valves, but if you have any issues as far as settings, as far as the PM program, these valves are going to fly open, and it's just going to cause damage within your system. The reason there is not a whole lot of control and telemetry on these valves is because the cost that it takes to add telemetry and controls. We've done a lot of different studies and evaluations, and we've come to the terms that once you add your sump, your PLC cabinets, and your electricity to the vault, you're somewhere around 15 to 20,000 plus to add telemetry to that vault. And that's not always feasible for what you're asking of this. With PRVs, you don't typically ever know that there's a problem unless there is a problem. And that problem is your PRV failed. It's usually we have water, we have a geyser, we have something blowing up. That's usually the biggest issue. There's so many benefits to having PRVs. I would argue that it's one of the most important assets within a water distribution system because it provides you the ability to control your source water. You can create operational efficiencies with them through pumping and gravity. Properly operating PRVs ensure nominal grade line pressures, and that just keeps the entire system safe. So with me, I always feel like knowledge and control within a system, a water system, is power. And that's where we come to, what's our solution to trying to save municipalities money, or maybe not always save them money, but not waste their money in water main breaks and inefficiencies. We have this great manufacturer that we have a residential meter, and we figured that, we kind of geek out on this stuff, and we realized that if you plumb this residential meter to the downstream of a PRV, it solves so many problems within your system. But not only that, it protects you from a lot of these that could come. When you go back to a PRV and its operations, if a valve's not operating properly, or you don't know what it's, the first thing you do is you manually close the ball valve, and it forces the PRV to close. The downstream ball valve will always force the PRV closed because it eliminates the ability for water to come off the cover. That's when we, kind of figured out and wrapped our heads around this KETOS wave. It's this ridiculously cool technology that acts as its own pretty much SCADA system. And like I said, when you install it downstream of the piping, it gives the PRV telemetry and control because it monitors pressures and flows, but it also has two-way shutoff. So instead of you manually closing that ball valve, you can remotely close that through this meter, which would make your valve come closed. Going into the meter itself, it's proprietary self-powered hardware. So, it has real-time monitoring. You can have your trending, you can monitor your flows, pressures. You can set your parameters to what you want within that software to tell you, hey, we have low pressure, hey, we have high pressure, and you could actually, what you want to do with that remotely. I've had years and years of getting called in at 2, 3 o'clock in the morning in snowstorms with high pressure complaints, trying to figure out which PRV has failed, but without eyes on it and control of that valve, you have to go out there. So that's a huge unaccounted for cost in human capital with people going out there, not to mention if there is cost to that. This meter is pretty cool because you don't need vault power, you don't need sumps, and you don't need PLC cabinets. It's hydro powered, so it's pretty much, it takes care of itself, but it gives you the biggest things that you need for that valve, and that's control and telemetry. So going into it, putting this KETOS wave downstream of the PRV, it does give you that remote ability to close the PRV while monitoring your flows and pressures. You could sit at home and close your valve. You could change your source water. You can adjust your pressures, whatever you need to do through your valves. When you're talking operational efficiency and pumping costs, to be able to control your pressure zones and your source water by keying in the PRVs that are coming off gravity and closing the ones that are coming off pump zones, that's a lot of money to save for a municipality that most people don't account for. With the pressures and flows part of it, you could always see your pressures and see where your high pressures are, and that's your biggest thing, because you can close your valve if you see high pressures, and you can kind of eliminate trial by error by that point. But also by monitoring flows, you could tell if your valve's working. If there's no flow through that meter, your valve's closed. If there is flow, it's working. And one of the big things with these valves is they like to be exercised. If they never run, they never operate, and that's where sizing becomes such an issue. That's where these ports clog up. That's where these valves fail. To be able to see if these valves are flowing, to be able to trend that data and see when the last time this valve was open, it's huge to maintain the accuracy, the operations of these assets within your system. When trying to evaluate, where does this fit in with just adding full telemetry to your valve, it was substantially cheaper. We say 50 to 75% cheaper, knowing the numbers, but it's actually, I think it's more towards the top end of that scale, closer to that 75% mark. Having crucial system data points within your system provides you a more efficient operation anytime. I truly believe that, and that's just from my experience in the industry and what I've always done. Having the ability to trend that data and have remote operations of these relief valves really make a super risky asset within your system less risky, and gives you control of that asset. So that's kind of where we're at with the PRV side. We want to go and open this up a little bit to some questions for any of you who might have them.
Thank you, Nick and John. I see a lot of different types of questions coming in here, and that was very informative overview, and I hope that all the participants found it as helpful, at least as much as I did. For some of the questions that are housekeeping general related, we will have the PowerPoint for you to download later, so you can go through the slides. You will have Nick, John, and my contact in a follow-up email if you want to learn more about KETOS Wave, as well as understanding some of these other concepts in depth. We will also have the training module of this recording separated out from the Q&A, just in case you wanted to use that recording as a reference. So with that, let me jump into a couple questions. Nick has been answering several, so thank you, Nick. Really appreciate it. One of the question here is, and Nick or John, either one of you can take this. Is there any reason to have a PRV upstream of a municipal meter and an RP backflow device in a commercial irrigation setting, especially when water pressures will never meet the RP device threshold limit? Nick, John, did any of you want to answer that? Let's see, I think you both went back to mute. So John,
Okay.
there you go.
So, yeah, as far as the backflow question on that, I would probably say we have a gentleman in our office that is, he's been 30 years on FEBCO, kind of wrote a lot of the specifications. Our skill set's kind of more geared on the control valve. Now, as far as in front of a meter, a municipal meter, I would say yes, there can be an application for that. And the reason why is because most of those have, where we've seen that is where you have a maximum working pressure, and you want to bring down that zone because that pressure may exceed what the maximum working pressure of the municipal meter is. So, since the municipality owns the meter, the application or the reason for it would be to protect that equipment. So there could be, yes. Got
it. No, thank you. And for some of the folks in the audience, there are additional questions that we will send via Q&A that Nick has already answered. I'll just kind of reiterate a couple of those questions in case you were thinking through them. What are some of the effects of water hammer on ACVs? Is there a good way to measure valve travel to make sure valve is moving through the whole range? After rebuilding a PRV, what is the proper procedure to put it back online? It would be great if you want to connect with Nick offline as well, because he wants to dive into it and have a longer conversation with you guys about it, based on the level of complexity and the details involved here. So these are some of the other questions that we answered. And Nick and John, I have one question, and both of you can probably have a different perspective based on your backgrounds. But when you think of your experience with Rep Masters and the level of engagement you have on a day-to-day basis with different municipalities, how is it impacting their business today in terms of operations because of this one specific application and this one specific issue?
Well, I'm super pleased that I had the opportunity to work for Denver Water. Am I echoing on your side, Bina, or no? Everything good?
No, it's good. I think one of you, if you have one of your volume, I think that's good enough. And then both of you could speak because you're kind of sitting close by. That would reduce the echo. So no, you sound great. Thank you, Nick.
So I've had the pleasure of working for Denver Water for a long time, and I got to see so many different aspects from the business side, the operation side, the construction side. And, I think one of the biggest things that I have to municipal operators out there is understand the risk that these valves pose to your system. I think understanding the damage that they can do to your system help you to know what you need to know about them. If you have something that can destroy your system so quickly and you don't know anything about them, it's probably a good idea to learn about them. Here at Rep Masters, we actually just started a service side to where we can actually help municipalities create PM programs and lockout tagout programs. And we do startup and commissioning. And, we want to be there as a resource to help municipalities understand, but also once you can understand them, maintain these PRVs. You could save so much money on pumping costs alone if you could understand how to do that. If you could figure out how to be efficient operationally, you would have the ability to save human capital costs. You'd have the ability to minimize water main breaks, and just to be completely efficient in your operations. Those are the biggest messages that I have in municipalities is learn these, understand them, and figure out how you can benefit from them and how to avoid any risks.
Oh, great. And Nick, one more over here, or John, if you want to pick this one. Basically, when a valve fails, what do I look at to determine whether it is the valve or the pilot valve that has failed? And so any comments there from you guys on that?
Yeah, when you're looking at determining whether a valve failed, there's a number of different processes you can use to kind of troubleshoot that. What we will just, you know, if you close that, the first thing we'd always do is close that downstream isolation valve. And if that valve doesn't go closed, then it can only be two different things. It can only be either you have a bad ball valve, which is probably pretty unlikely, although it does happen. But usually that will kind of determine if that's something going on inside of the valve or if it's something going on in the pilot line. Another thing you could do would be to go ahead and make an adjustment on it. Because if the pilot, probably more common than something inside the valve, I would say, is going to be, unless that valve's been operating and you know it's been operating at a low percent of VP, is going to be debris being on that pilot. But you wouldn't be able to tell that if you close that ball valve, the valve goes closed. Now we've kind of, you know, isolated or we know that valve, something's probably going on in that pilot line. And more than likely, the second place to check would be that regulator. And you can, if you have isolation valves, and you can lock that valve into place by closing both the downstream and upstream at the same time, or closing the ball valve on the cover will freeze that valve in position. Now you won't be regulating while you're doing this check, but at least you won't be shutting off flow. And then going into that pilot, you can use, there's a nut on the bottom, and you can take the cover off and you can just clean out that debris by the seat. That's usually what we see on a pilot is debris blocking that seat from closing on the pilot. So when that pilot goes closed, it's still letting flow, you know, through or past the pilot.
Got it. Thank you, John. One more question here. Are there any recommendations for rehabbing an old valve body that has had probably pitting or some enamel removal? Any thoughts on that?
Typically, if you're getting pitting on the body itself, that's good signs that it's time to get a new valve. If you're having damage to the internal parts, the stem kit assembly, the seats, things like that can be replaced. But the issue is once the epoxy is ripped off to that inside of that body, that's where you're going to start getting the real damage to the valve body itself. And it'll only continue to get worse unless you can pull that valve body completely apart and re-epoxy it. And that's not something that I would recommend because the manufacturer epoxies a valve based on AWWA standards. And, you know, I wouldn't go through the hassle of re-epoxying a valve. I would just recommend getting a new valve.
Got it. I know we're coming up on time here, so maybe one last question to both of you. You know, as we wrap up here, and I know majority of the audience are operators from different municipalities and utilities, what is your, you know, as experts in this field, what would be your sort of message or anything that you can give them as a guide in this regard specific to PRVs? Nick, you want to go first and then John?
Well, I mean, I always like to say, you know, lean on those who know and try to learn from them. There's a lot of great, you know, I work with so many good people at Denver Water that know so much about PRVs and, you know, being able to lean off each other for things that I didn't know or things they didn't know, it made us more knowledgeable. And that's why we're here. I've worked with a lot of municipalities who know absolutely nothing about PRVs and it's not uncommon. So like I said, whether it's control the valves, knowledge is power, you know, lean off those who have the knowledge and gain what you can from them.
Nicely said.
You know, one thing I would say this is something in the class is, you know, we're kind of at a crossroads in our infrastructure. There's a reason why we're looking at I think we've been upgraded from a D- to a D for drinking water infrastructure. And, you know, the bottom line is what we're currently doing right now is it's not working. And, you know, I feel that the job that everyone in this, especially on the municipal side, the utility, municipal workers, your guys' job is just as important as first responders, firefighters, military. And I say that in 100% honesty because, you know, think about how long we could go. We all saw what happened during what's going on with COVID. Imagine if the water gets shut off. And we saw people going crazy over toilet paper. So turn people's water off, as you guys know, on shut-off day. So it's a thankless job. Before I got into this industry, if you asked me where water came from, I would have said the faucet. So, and I think probably everyone's like that. And the reality is, one way I think we can get out of this is to understand we got to do things different. And there's a lot of there's great manufacturers and there's bad manufacturers. And the ones that are going to make it and be the ones that are the ones who are going to work with the municipalities, and they're going to be there to be that resource and the guide. Bring us your problems. There's a lot of great manufacturers, and you can tell with how eager they are to find out what your problems are, and then help develop products that address those needs. Because our populations are growing, but as you all know, our operating budgets are not. So it's going to require us to be outside the box and be more efficient. And in every aspect, just some of these, what we went over, imagine, you know, if we knew that every single, 80% of our valves were oversized. We talked about the drastic difference in cost. If we knew what those valves were operating at, maybe when we go to replace that, we can kind of end that cycle and put the properly sized valve, reduce costs there by 50%, depending on how many PRVs you have in your system. That's a lot of money. So, that's really, I guess my parting words would be, work with those and do your research and reach out. If we don't have the answer, then we'll point you in the right direction. If it's not us, it makes no sense to offer a solution that's not gonna work. So I guess that would be what I have.
No, thank you, John. Couple of quick questions. I'll just leave it at a comment here. So there were multiple questions on whether KETOS can work in different environments. So the KETOS wave does work whether it doesn't need a cellular service. It actually uses LoRa, so long range, low power mesh networks. And then basically has a gateway to integrate for all the backhaul communication. So we can, depending on your need, we can understand how your setup is, and both Rep Masters and KETOS can work together to, if you have a census base, that was just a question someone specifically asked about a fixed base like census, so that was a response. But we have different protocols in terms of how we would integrate with, say, existing meters or not. But KETOS Wave does not need to have a cellular service in terms of where it's deployed as a sensor node. There were also some questions about self-power, how happy to engage and answer those questions. Nick, John, and I will compile a lot of these questions into an FAQ or a response and send it back to all attendees so that you have that for your reference offline as well. I know we're on the top of the hour here. Thank you all very much for joining. We will have smaller sections, as mentioned earlier, for the recording. And I really hope we get to stay in touch and we embark on this path of being your trusted consultants and guides. I know how valuable your time is, and we really appreciate your presence with us. So thanks again, and have a great rest of the day, everyone. Cheers. Thank you.
Thank you all.